He's in Fast and Furious.
My friends, as promised before lunch, we were going to take on the 4 quantum numbers from the Schrodinger equation. This shouldn't take us very long at all. We'll be done with this. I have listed what the 4 quantum numbers are over there. You may have had a Chem 1 teacher that went through these, and then you might not have. Different teachers would kind of approach this topic differently. But there are 4 numbers. Here's the first 2, the n value and the L value. The n is, we call it the principal quantum number. It really just tells how far from the nucleus the electrons are. The bigger the n, the farther out it is. This is very much like what Bohr's model had, where n represented the rings. Now there's a term in here. I know you're writing, but I never did officially define the term orbital. An orbital is a region where we expect to find electrons. I use that word a lot. We ought to have a working definition of orbital.
Wait, is that L?
It is an L, yes. This one, I know it looks like a 1. Or an I, possibly without the dot. It's an L. Now, when I'm writing these, I always make the L a cursive L because I don't want it to look like a 1.
Wait, is that also, how is that not 1?
Where? Up here?
No, that's 1, sir.
Oh, okay.
That, like, next
The
to
n
P.
minus 1?
Yeah.
Yeah, that's a 1. All right, maybe I do have to dump the font.
I like
Yeah, me too. If we didn't have 1s and L's and 2s and Z's, it would be fine.
it reminds me of Siddharth's handwriting.
Oh, no, it's nothing like Siddharth's
Because
handwriting.
can't even read Siddharth's handwriting.
My hair has improved a lot from like beginning.
I didn't read your writing last year, Siddharth. I can't read it this year.
Oh, I grew up quickly, so
Yeah.
a lot of
Yeah, blame it on the speed, Siddharth.
Now, whether or not you did the quantum numbers last year, I know that you learned S, P, D, and F. These symbols come out of the second quantum number, which is, the name is L. The L value depends, L is, officially it's called the angular momentum quantum number, but I think of L as the sub-level. Within energy levels, there are sub-levels. Energy levels are kind of divided up. According to Niels Bohr, energy levels were just rings, concentric rings around the nucleus. Ellen?
What is n minus 1?
Oh, that's the highest possible value of L. So within an energy level, which is defined as n, you can have sub-levels, which are regions within an energy level. The values could be 0, 1, 2, 3, up to n minus 1. So if we're in the third energy level, the possible L values would be 0, 1, and 2. Because if the n is 3, then 3 minus 1 is 2, so the highest L value would be 2. Now the energy sublevel describes what the shape of the orbital is. Remember, the orbital is this. It's a region where we can find electrons. It turns out that every orbital can hold 2 electrons. Does this kind of come back to you? Do you remember the letters S, P, D, and F? Yeah. If L equals 0, we call it S. If L is 1, we call it P, like that. And on the periodic table, just from your memory from Chem 1, I would expect that you would remember that the rows on the periodic table are numbered 1, 2, 3, 4 through 7. They're numbered along the side. It's kind of inconspicuous, but they're there. And then where are the S's? Over on the left side of the periodic table. The first 2 families are the S's. And then the P's? Over on the right, the last 6 columns are the P's. And in the middle of the periodic table, those lower families are D's. So the numbers on the row, they represent the energy level. So for in the first row, that's the first energy level of electron. Second row, second energy level, like that. And then it's broken up by sublevel. So that, I know that you have some recollection of some of these numbers. You don't have to do anything with this. I just want you to see what, according to the Schrodinger model, what these energy sublevels look like. If you have an L equal to 0, that's called S, and S sublevels are just spherical in shape. That means the electron would be somewhere on this green region with a high probability that it's on the green region, just floating around somewhere. We don't think it spins around, revolves around the nucleus. It's just doing something in it. We don't know anything about its motion. We just think it's that distance from the nucleus. Now when you have the second energy level, that would be on top of the first energy level. So you'd have electrons in there, the first 2 electrons would go in there, that's the first energy level, that has full. Go on to the next one, and they would be on the outside of the green. And in between the first energy level and the second energy level, we call that a node. A node. If you've had physics and you've gone through waves in physics, you might have learned that a node is, when you have a wave, a node is the part of the wave that does not move. And so when we have a node, when we're describing electrons as waves, that means the electron cannot be there. It can't be part of the wave in that spot. So between the energy levels, we call that nodes. So that's what the S looks like. S is spherical. That's not why we call it S, but it does turn out to be. P orbitals are dumbbell shaped. And it turns out that there are 3 different P orbitals in every energy sublevel. They're all the exact same energy. We call that degenerate P orbitals. But there's one along the x-axis, one along the y, and one along the z-axis, and they're all perpendicular to each other. This would be a P sublevel all together without breaking it up into 2. So the nucleus is at the origin every time. So if the nucleus is right in here, we would have an S that's spherical, and then another S that's spherical. And when we get to 2P, then we get into this dumbbell shaped. There's 3 different dumbbell shaped orientation. Again, you don't need to know anything. You might just do well to know that S is spherical in shape and P is dumbbell in shape. And when I say dumbbell, it's like you got a thin spot in here and then the bulging part out there. And so in this region somewhere, 2 electrons can be found. And in this region, 2 electrons. In this region, 2 electrons. Like that. So P's can hold a total of 6 electrons. That corresponds with the 6 columns over there in the periodic table. Just for the sake of getting a smile out of it, these are the D's and the F's, what they look like. When you have a D sublevel, that means that L equals 2. The higher the L value goes, the more complex the shapes get. So we go from dumbbell shaped in P to what we call clover shaped with the D's. There are 5 D orbitals. They look like this. They're all the exact same energy. They don't all look exactly the same. We got the kind of goofball here, the dumbbell with the donut around it. And then the other ones are kind of clover shaped. So there's 5 of them, and we'll find out the significance of that soon. The F's are even more wacky looking, and there's more oddball shapes, I guess, in the F's. Although the top 3 are all very similar, and then the bottom 4 are all kind of very similar to one another too. You won't be asked anything about D's and F's, either on this exam in the class or on the AP exam. They're not going to. They might ask you about P's and S's, but not about D's and F's. Yeah.
So like those orbitals, does electrons only move within like the outer edges, or like?
No, somewhere like this would hold 2 electrons. So somewhere in the pink is a space for 2 electrons. We don't know where. The Heisenberg uncertainty principle says we can't tell where those electrons are. We just know they're in there somewhere.
So they're like
in that region. Yeah, we think that they're moving, but we can't track their motion. Yep. Yeah. So the F's can hold 14 electrons, 2 in each, and there's 7 orbitals there, so they can hold 14. Okay, the next quantum number is called M with the subscript L, and we just normally call it M sub L. And the M sub L is what dictates how many orbitals there are. That's why, like, the P's have 3 orbitals, the D's have 5, and the F's have 7, is because of the M sub L number. It describes the orientation of the orbitals. Guess?
Next to the m sub 1 equals, is that negative 1?
Yes, that's negative. No, that's negative L. And this is m sub L, not m sub 1.
Oh.
M subscript L. So m sub L goes from negative L up to positive L. So just a quick little breakdown. If L equals 0, we call that S. M sub L would equal 0. It goes from negative L to positive L. If L equals 1, we call that P. M sub L could equal negative 1, 0, and positive 1. If L equals 2, we call that D. M sub L would go from negative L to positive L. Negative 2, negative 1, 0, 1, and 2. Like that. So, and it can keep going from that. If you go to L equals 3, M sub L will go from negative 3 to positive 3. But these values, the value of the number itself doesn't help us to really know anything. But the number of values M sub L can have. You know how the S was spherical in shape? Within an energy level, there's one S orbital. It's spherical in shape, and that's it. For every energy level, if you have a P, there's 3 P's, one along the X, one along the Y, and one along the Z. So the number of M sub L values tells you how many orbitals are in there. With the D's, remember there were 5 D's. 1, 2, 3, 4, 5, like that. So that's consistent with what we were talking about. So M sub L tells how many different orbitals can be in that energy sublevel. And one final thing, that's the fourth quantum number, the M sub S. M sub S represents the electron spin. Because an orbital is a small place for 2 electrons to be shared. Electrons do tend to repel each other, so how could 2 negative electrons occupy and live together in a very tight space? Well, the only way that can happen is if they're spinning and they induce magnetic fields for themselves. So the M sub S value can be either positive 1/2 or negative 1/2. And mathematically, why 1/2? That comes out of the Schrodinger equation. You have to solve it, and that's what it would give you.